So linear algebra is the hidden engine behind AI. Linear algebra is the hidden engine behind AI. So if we look at like what powers the modern AI, data as geometry. So in the world of AI, data isn't treated as text or images. It is treated as geometry. Because you know that in artificial intelligence, we try to find the patterns in the data. And if we are trying to find the patterns in the data, we are considering data or we are treating the data as geometry and not as text or images. So in the world of AI, we treat data as geometry to identify patterns in it. So that is what is the core philosophy behind the modern AI, finding patterns in the data. So if we treat data as geometry, it is possible for us to find the patterns. And to treat data as geometry, linear algebra plays the role. So linear algebra is the framework that allows computers to see patterns in high dimensional space. So we can see patterns in high dimensional space using linear algebra. Linear algebra is the framework. So if we talk about the core components of linear algebra, which powers the modern AI. So the core components is the how. So we have vectors. So vectors are the basic building blocks. Every piece of data, like a word, a pixel, or a user preference, is converted into a vector. So vector, you can treat it like a list of numbers. Now that list can be a horizontal list or a vertical list. So we can have a row vector, we can have a column vector. So list of numbers is a vector. So basically, whether we are talking about a word, a pixel, or a user preference, like every piece of data is converted into a vector. So this places the data at a specific point in multidimensional embedding space where similar items are mathematically closer. So what we do, if we represent the data in form of vectors, then in a multidimensional embedding space, automatically we will see that the items which are related to each other, which are closer to each other, mathematically also they will be close. Like let us suppose if we have data related to dog, so it will by default be occupying, it will be close in this region, and the data points related to cat will be falling in this region. So if we represent the data as vectors, then because of that, automatically the vectors in a multidimensional embedding space, similar items, they will fall closer. They will be mathematically closer to each other. And hence, this is a very powerful concept which enables us to find patterns. And now see, we already saw that with linear algebra as a frame. So linear algebra is the framework to represent data as geometry. And now we are getting a feel of it. Because if we represent the data as vectors, by default, similar items, they will be mathematically closer to each other. So we are treating data as geometry. So if we talk about the core components of linear algebra, we have matrices. So the core components of linear algebra which powers the modern AI, matrices is one of the core component. So you can think of matrices as the memory of the AI, the AI's memory. A matrix is a collection of vectors. And since it's a collection of vectors, matrix represents a data set. In a neural network, the weight matrix stores everything the model has learned. So in neural networks, we may use of something called as the weight matrix, which represents everything which the model has learned. So weight matrix stores the learned information. So when you input data, it interacts with these weights. So input data interacts with these weights in the weight matrix. Now the next core component of linear algebra powering the modern AI is the transformations. So see, vectors and matrices, it is more of like representation. Vectors and matrices, they are used to represent the data, but transformation is the action, processing the data. When an input vector is multiplied by a weight matrix, it undergoes a linear transformation. So whenever we multiply a input vector with a weight matrix, then the result is a linear transformation, and that transformation can be rotation, scaling, shearing, and this allows this transformations allows the AI to filter out noise and highlight relevant features. So whenever we perform operations on the vectors and matrices, whenever we perform operations, we are basically performing the linear transformations. And with this linear transformations, we can filter out the noise, we can highlight the relevant features, and so on. We also have a core component called optimizations. So optimization is also a core component of linear algebra, which powers the modern AI. So see, AI, it learns by minimizing the error. Artificial intelligence, it learns by minimizing the error. So optimization makes use of calculus plus linear algebra. So by calculating the gradients, the system exactly determines how to nudge the numbers in a matrix to make the output more accurate. So that is what the gradient descent is, which is an example of a optimization technique which makes use of both the calculus and the linear algebra. So linear algebra also plays a role in optimization. So by calculating the gradients, we can find like how exactly we should update the numbers in the weight matrix to make the output more accurate. So if we talk about the core components of linear algebra, so eigenvalues and eigenvectors is also a core component of linear algebra which powers the modern AI. Eigenvalues and eigenvectors. So eigenvalues and eigenvectors, they identify essential directions in data. They tell the AI which features are the most important. They show most important features. For example, if we talk about facial recognition, eigenvectors are basically the eigenfaces, represent the most distinct features that separate one face from another. So eigenvalues and eigenvectors are like some very powerful components of linear algebra. They identify essential directions. They show the most important features to consider. Like if I talk about facial recognition, in a face, we can have so many features. But if we make use of eigenvectors, then we will have eigenfaces. So eigenfaces are the faces containing only the most relevant features, eliminating all the noise, all the unnecessary features, we are getting rid of it. So that is what eigenface. And eigenface, we can get it using the eigenvectors. Similarly, singular values, like singular value decomposition, is also a core component of linear algebra which powers the modern AI. So this is the ultimate tool for compression and noise reduction. So if you're talking about compression and noise reduction, then singular value decomposition is the ultimate tool. Singular value decomposition allows a system to take a messy matrix and break it down into its most important parts, discarding the junk data without losing the core information. So singular value decomposition, it's a technique of linear algebra which breaks down a messy matrix, discarding the junk data and keeping the core information. So now we looked at the core components of linear algebra. Now we will look at the functional benefits of linear algebra, the why. Like why we should use linear algebra, or why linear algebra is modern, powering the modern AI. The functional benefits of the linear algebra, like why we should use linear algebra, or why the linear algebra is powering the modern AI. So representation. So linear algebra provides a universal language. Whether you are translating French to English or identifying cancer in a X-ray, so whether you're translating, identifying, doing some kind of a recognition, linear algebra represents both problems as operations on numerical arrays. So linear algebra provides a universal language for representing the data. So regardless of the operation you are performing, if you represent the data in the form of vectors and matrices, you can solve problems. So that is what the linear algebra is. So now it's very clear that why linear algebra powers the modern AI, because linear algebra provides the universal language to represent the data. Computation. If we talk about modern hardware like the GPUs, they are specifically designed to do one thing extremely well, that is the matrix multiplication. So modern hardware, they make use of like GPUs. So GPUs are designed for matrix multiplication. GPUs are designed to carry out billions of simultaneous calculations. So linear algebra allows us to perform billions of calculations simultaneously rather than one by one. So now it's very clear to us that linear algebra, why it powers the modern AI, because it provides the universal language to represent the data. It provides the computational framework, because modern hardware like the GPUs, they make use of linear algebra, they make use of matrix multiplication to carry out billions of simultaneous calculations. Structure. So linear algebra, it turns chaotic data, unstructured data, into a rigid geometric grid. Because with linear algebra, we are treating data as geometry. So linear algebra, if we represent the data using the concepts of linear algebra, then we are turning the chaotic unstructured data into a geometric grid. This structure allows us to use concepts like distance and angle to find invili- relationships between data points that would be invisible to human eyes. So once we convert the chaotic unstructured data into a geometric grid, we can use concepts like distances and angles to find the invisible relationships between the data points. And this is how the linear algebra is powering the modern AI. And also, we have efficiency. So techniques like dimensionality reduction using SVD, PCA, like singular value decomposition, or the principal component analysis, it allows the AI to process massive data sets by focusing only on the components that matter, drastically reducing the amount of memory and power required. So dimensionality reduction is also a concept of linear algebra. So with linear algebra, we can also achieve efficiency, wherein we can process massive data sets by drastically reducing the amount of memory and power required. So now it's very clear to us that why linear algebra is powering the modern AI. Linear algebra provides the universal language to represent the data. It provides the computational framework like the matrix multiplication, using which modern hardware like the GPUs can carry out billions of simultaneous calculations. Linear algebra provides structure, like it can turn a chaotic unstructured data into a geometric grid, structured data. Using linear algebra, we can treat data as geometry, which allows concepts like distance and angle to find invisible relationships between the data points. And linear algebra, it also provides efficiency, wherein we can use the concepts of dimensionality reduction to process massive data sets using reduced memory and power consumption. And hence, linear algebra is the hidden engine behind artificial intelligence.